So we can investigate crystalline structures using X-ray crystallography. What are these structures? When we refer to a crystalline lattice, we're talking about the regular arrangement of atoms within a crystalline solid. And the word lattice here is a lot like, if you think about a garden lattice, right? Oops. Hopefully that didn't screw anything up. Where you have, kind of a trellis thing, it's a lattice, and you have ivy climb up on it. So here, when we're looking at a crystal lattice, where these slats would interact or intersect on this trellis, that would be where an atom, an ion, or a molecule is, where the particles are. And the particles are going to arrange themselves in a way that minimizes their energy. And we're not going to go into why this particular structure is a minimum energy. We're just going to identify the different kinds of structures. So to look at this structure, we think about a unit cell. And a unit cell is the smallest piece of the crystal that, when repeated in 3 dimensions, gives you the entire crystal lattice. So looking at a 2-dimensional lattice here represented by these circles, if I take this dark red box here, which is going from the center of these 4 spheres, and including this one in the middle, if I take that square and repeat it in all dimensions, I'm going to get the entire lattice. There's not a smaller piece that you can do it with. There are larger pieces. You could take this big square and repeat it, you get the same thing also, but we're always looking for the smallest. Okay? The circles represent the lattice points. That'd be a particle, atom, ion, molecule. Any questions yet? This is a little bit like, you're sitting in the bathroom, public restroom, and you're looking at the tile pattern on the floor, right? And some of them, there's lots of different tiles, and you look at them for a while, and you see, there's a pattern here, right? That's kind of what we're looking at here. There are lots of different types of unit cells. We're going to look at one. So we're going to look at a cubic unit cell. In a cubic unit cell, the sides are squares, so the lengths of the edges are equal, and all of the angles are 90 degrees. There are a lot of other unit cells. And these sorts of things like triclinic or monoclinic, rhombohedral, those give rise to some really beautiful crystals. But we're just going to look at this cubic one, and then later take a very quick peek at a hexagonal one. In looking at the unit cells, you're going to see spheres of different colors, but we are representing all of the atoms. All of the spheres represent the same type of atom. The different colors do not mean different elements. It just is so that we can see it better. It's just for visualization. And a couple of quantities that we refer to with unit cells are coordination number and packing efficiency. The coordination number is just the number of atoms with which each atom is in direct contact. So how many close neighbors does the atom have? The packing efficiency is the percentage of the volume of the cell that's actually occupied by spheres, as opposed to how much is empty space. And it can't be 100% because there's no way to pack spheres together and not have empty spaces between them. If you have a higher coordination number, you have a greater packing efficiency. Ideas like this apply to things other than just crystal structures. Fruit packing. You're packing spheres into a box, and how can you get the most mass of oranges into a single box? Packing efficiency becomes important. I don't know why that slide's blank. Oh, there's an animation by accident. Cubic crystalline lattices. So this is a summary, and we're going to talk about each of them briefly. Here we have the simple cubic Body-centered cubic, face-centered cubic. We see these vary in the number of atoms per unit cell. The coordination number is different, and the packing efficiency is different. And we can illustrate those like this, but that's probably not very helpful at this point. So let's look at a simple cubic unit cell. Here we have one atom at each corner. And so here the unit cell just starts at the center of each of these atoms. And so within this one cell, you've got an eighth of this atom, and an eighth of that atom, and an eighth of this atom. And so total in this one cell, you have one atom. You have 1/8 of 8 different atoms. The atoms touch along the length here of a side. And so this side L, we can express in terms of the radius of the particles. This is the radius of one particle, and then the radius of another particle. And so the edge length is equal to 2 times the radius of a particle. Any questions about that? The other two are a bit more complicated. I do want you to understand this one. And then the other ones you can just say, well, because she said so. So there's that cubic unit cell. If we draw the rest of those atoms, we see we've got 8 atoms here, but the unit cell is going from the center of them, and so the unit cell is in the middle here. To look at packing efficiency and coordination number, we're going to look at one of those atoms and see, well, how many nearest neighbors does it have? Because here, this atom is touching this one over here, and that one behind it, and this one above it, and then there's also some coming on the other side, right? So here, this atom is touching that one, and this one, and this one, and that one, and this one, and this one. So it's touching 6 other atoms. That's the coordination number. And we can calculate the packing efficiency by calculating the volume occupied by the atom. There's one atom in there, so we can figure out the volume in terms of R. And then we can calculate the volume of the cube and look at the packing efficiency. So let's calculate a packing efficiency in a 2-dimensional lattice. So here we have a lattice, and the unit cell we're looking at here is in white. So if that is repeated over and over again, where all these black squares are, we get the whole lattice. So the packing efficiency we want, here we're not looking at volume, we're looking at area, right? Because it's 2-dimensional. Area of atoms divided by the area of the unit cell times 100 is going to give us the packing efficiency. So we can label the radius as R, and then the edge length, L, is going to be equal to 2R, right? Here's 1R and 2R. So what's the area of the unit cell? What's the area of a square? The length times the width, right? The area of the cell equals length times width, which is 2R times 2R. So that will be 4R squared. Okay with that? And then what's the area occupied by the atoms? Well, right there is 1/4 of a circle, right? And here's 1/4 of a circle, and here's 1/4 of a circle, and there's 1/4 of a circle. So area of the purple circles, there's one circle in there, right? It's just cut into pieces. What's the area of a circle? Pi r squared. So area of the atom is going to be pi r squared. That's just a geometry equation. So to find our packing efficiency, we want to take the area of the atom, pi r squared, and divide by the area of the cell, which is 4r squared, and then multiply by 100. What's always going to work out is that the r's are going to cancel out because we're measuring both of them in terms of r. So r squared cancels r squared, and this ends up with being pi over 4 times 100. And please do not shorten pi to 3.14. You have a button on your calculator. Use it. Of course, I can't find it right now. Where'd you go? There it is. Pi divided by 4 times 100. Technically, this would be an exact, well, as exact as you can get with pi. Technically, it would have unlimited number of significant figures because the 4 is exact, the 100 is exact, and pi is what pi is. But we'll just go for kind of a reasonable number and say that this is 78.54%. That tells me that any region here, I look at a big area, 78.5% of it is occupied by the purple circles, and the remainder is empty. Any question? It'll have no units, right? For percentage, percent really is the unit, because we're taking one thing and dividing it by another with the same unit, and the units always cancel out. Any questions? 78.5, they rounded it a little differently. Another one is called a body-centered cubic unit cell, and here we have an atom in the middle. So there's a body in the middle of the cell, so the body centered, and then we have parts of 8 atoms at the corners. So it's like you push those guys apart and stuck one in the middle. Here it becomes a little more complicated to calculate the edge length in terms of r. Here's the derivation if you're interested. Bottom line is it comes out to this. The length is equal to 4 times the radius of the atom divided by the square root of 3. You don't have to memorize that. Looking at different views, here's the actual unit cell. Here's with all of the neighboring atoms intact. And again, the purple and the gold are the same kind of atom. It's just hard to look at if we don't use 2 different colors. And so then coordination number, we're looking at this guy in the corner and how many does he touch? So these guys touch diagonally through the cell, not along the edge. Here the coordination number is 8. We can calculate packing efficiency is a little higher, it's 68%. Inside one of these cells, we have that gold one in the middle, that's an entire atom. And then at each of the 8 corners, we have 1/8 of an atom. So there's a total of 2 atoms in this cell. Okay, a body-centered cubic unit cell has an edge length of 588 picometers. What's the radius of the atoms composing the unit cell? And this is a conceptual question, so we're not supposed to have to do a calculation here. So what we have is we've got these guys at the corners, and then we've got one in the middle. That's a pretty ugly picture there. And it's telling us that this edge length is 588. And it's asking, what's the radius? What's this? Because of this one in the middle, the guys at the corner don't actually touch like they do for the simple cubic unit cell. And so 588 must be larger than 2 times the radius, right? So we can look through these choices and kind of eliminate things. Well, it can't be 588, right? Because if this was 588, then the cell couldn't be 588, so that's not right. And we got 294, 255, and 208. Well, if we double those, 294 is times 2 is greater than 588. That's going to be close to 600, right? And so that's probably not the right one. And then we've got 255. Let's see. Times 2, this would be 510. And this is going to be 416. Honestly, standing here, I'm not exactly sure what the author is expecting you to think. Obviously, you can do the calculation, but you're not supposed to have to do the calculation here. So 510 means that the gap in here is relatively small. The gap for this one would be bigger, and so I'm going to guess C. And I don't actually have the answer here, so I'll have to calculate it real quick. Uh, 4r over the square root of 3. 4 times 255 divided by the square root of 3, 588. So I think in the future, I'm not going to do this example because I don't think it was helpful. An atom has a radius of 138 picometers and crystallizes in the body-centered cubic unit cell. What's the volume of the unit cell? So, cubic unit cell, body-centered, L is equal to 4r over the square root of 3. Because you look it up or it's given to you in the problem. Okay, this is saying that the radius of an atom is 138. So radius equals 138 picometers. And it wants the volume. So these unit cells are cubes. And so each side has a length of L. So the volume of the cube is L times L times L. Everybody okay with that? So that's 4r over the square root of 3 cubed. They're giving me the radius in picometers. They're asking me for the volume in cubic centimeters. You could calculate the volume in cubic picometers and then convert to cubic centimeters, but I find that a lot of people have trouble with that, even though we learned about it in the first chapter. I think it's easier to convert to centimeters first and then stick it into the equation. So if my radius is 138 picometers, what does pico mean? it's smaller than nano. Nano's 10 to the minus 9. Pico's the next one, 10 to the minus 12. So that's the same as 138 times 10 to the minus 12 meters. Because 10 to the minus 12 is what pico stands for. And then if I want to convert this to centimeters, put centimeters on the top and meters on the bottom. 1 centimeter is 1 times 10 to the minus 2 meters. The meters cancel out. And let's just go ahead and use the calculator. .38 times 10 to the minus 8. Centimeters. So to find the volume of this unit cell, I'm going to plug that R into the equation. So I have 4 times 1.38 times 10 to the minus 8 centimeters divided by the square root of 3, and that whole thing is cubed. So I'm coming up with 3.24 times 10 to the minus 23rd cubic centimeters. Any questions? The ACS final exam does typically have some questions about unit cells. So I definitely don't want to be skipping this. 3.24 times 10 to the minus 23. The third type of cubic unit cell is the face-centered. And here what we have on the side of this, we have an atom centered on the face. Okay, instead of an atom in the body in the middle, we have an atom on the face. And again, we have some calculations, and that graphic is missing some things. What the heck? Yeah, so there's some graphics missing here. I think it's supposed to be like this. L is equal to 2 times the square root of 2 times R. This one's a little more straightforward. We've got a diagonal where we can see the radii are touching. But again, only look at that derivation if that's the sort of thing you're interested in. I got lost. Here again is our face-centered. This becomes much more complicated now when we try to draw the whole thing. And you look in here and you try to figure out the coordination number, and it gets to be pretty challenging. I just trust them when they say it's 12. And the packing efficiency here is 74%. So this is a more efficient way of putting atoms together into a crystal. They're going to be packed more densely. Chromium crystallizes in a body-centered cubic unit cell. The radius of a chromium atom is 125 picometers. Calculate the density of solid crystalline chromium in grams per cubic centimeter. And this is kind of a out there sort of problem, but it's also really cool. So we've got a body-centered cubic unit cell. What's a little tricky about this problem is we just talked about the face-centered, and so we tend to want to do the face-centered. It's the body-centered. So for the body-centered cubic unit cell, L is equal to 4R over the square root of 3. Again, I do not expect you to remember that. The radius is 125 picometers. And we're supposed to calculate the density of crystalline chromium. So, what is density? Mass divided by volume? Yeah? So what we're going to do here is we're going to look at a cubic unit cell and see if we can figure out what's the mass of that and what's its volume. Well, the volume isn't too hard. We've already calculated that once. The volume is L cubed, right? So the volume of the cell is equal to L cubed 4R over the square root of 3 cubed. You just need to put the number in there. What's the mass of this? How many atoms are in that unit cell? 2. The body-centered, there's one in the middle, right? There's one atom in the middle, and then we've got atoms at the corners, right? So the atoms at the corners, there's 8 eighths, so that's one atom plus the one in the middle, 2 atoms. So what we want is the mass of 2 chromium atoms. We haven't thought about things like that for a while, but we should be able to do that. 2 chromium atoms. Well, how many moles of chromium is that? Can we convert from atoms to moles? Sure. We need to dig out Avogadro's number. And that gives us the number of moles of chromium, and then we can use the molar mass of chromium, which we get off the periodic table, 51.9961 grams per mole. So 2 divided by Avogadro's number times 51.9961. This is the mass of 2 atoms. 1.7. Oops. 72687 times 10 to the minus 22 grams. We expect that would be a really, really small number because 2 atoms don't weigh very much, right? And then we can go down here and finish out our volume calculation. Again, they give the radius in picometers, and then they're asking for information in cubic centimeters. So the radius is 125 picometers. That's 125 times 10 to the minus 12 meters. And convert that to centimeters. And you can do this on your calculator. You can also look at this and say, well, I've got minus 12 and minus 2, and so this is going to be equal to 125 times 10 to the minus 10 centimeters. Not standard scientific notation, but it's going to work fine in the calculation. You do it on your calculator, and you come up with 1.25 times 10 to the minus 8 centimeters. Either one. 2.40 times 10 to the minus 23rd cubic centimeters. So here we have our volume, and here we have our mass. So we can plug those into our density equation. .72687 minus 22 divided by 2.4056 minus 23. So I'm getting out 0.71, no, not 7.18 grams per cubic centimeter. Crazy how you get like a regular number like 7 out of that big mess? Hey Siri, what's the density of chromium?
The density of chromium is about 7.14 grams per cubic centimeter.
Look at that, it's pretty close. Any questions? These sorts of calculations are not a big part of chemistry, but there will be something on the exam. You can definitely pass the class without being able to do this calculation. This sort of question I would encourage you to work on. How many atoms are in the unit cell in a face-centered cubic structure? I didn't really talk about that. I showed you the picture, but then. So we've got one on the face, and then you've got the guys at the corners. Instead of looking at my crappy drawing, let's go back and look at a good drawing. This one. So we have 1/8 of an atom at each of the corners, so that adds up to 1 atom. And then we have half of an atom on this face, half on that face, half on that face, half an atom at 6 faces. So how many atoms in the face-centered cubic structure? 4. How many in the body-centered? 2. How many in the simple cubic? 1. Okay. 14s is ridiculous. So, any questions? We're talking about the same stuff now in kind of a different way. Another way to think of the crystal is in terms of stacking atoms in layers. So think of your favorite spherical object, whether it's an orange or a baseball or marbles or whatever. And imagine putting these round things into a box. And there's different ways you can pack them in, right? The simple cubic structure is one where we have a layer of atoms, and they're lined up in a grid, like they're square, right? And then the next layer, the atoms are right on top of each other. And so in any direction, you've got just rows. Now this is not what things like marbles or oranges naturally want to do in a box, right? But you can get them to stack like this. You'd have to have something constricting them, and it would have to be full, right? Because otherwise what's going to happen is this marble or orange is going to fall into the divot created by the ones underneath. And we're going to see that that's going to come in to these other structures. So this structure has a lot of empty space in it.
Do we need to be focused on the outside forces affecting these crystals?
No. No, outside forces affecting it really only comes into play when we're talking about marbles or oranges or something. How do we get them to stack like this? Well, there'd have to be something holding them that way. The reason that some atoms stack like this is very involved is because they're lower in energy, and a lot of times it has to do with relative sizes and all kinds of other very complicated things that we don't have to worry about. More efficient way to pack marbles or oranges, let's just stick with oranges, it's really oranges, is here what we've got is this row is offset from that row by half of an orange. See that? And so they're staggered together and they fit more snugly into each other. That makes sense? See what I'm talking about? This is what the other one looked like. Where they're lined up with each other in both directions. Here, they're not lined up across, they're staggered. And they fit together more tightly that way. Then when you go to put the second layer on, instead of having the second layer directly above the first layer, you let this second layer move over and fall into the indentation from the three atoms below it. So these three atoms here, there's going to be a little indentation here, kind of almost a nest for the next orange to sit on. And so we're going to let this second layer sit in all of those little indentations. It's naturally what it wants to do. And so layer B is offset from layer A, not right on top of it. These are called closest packed structures because unlike the simple cubic, this is the closest you can pack them. There are two closest packed structures. They have the same packing efficiency. They have the same coordination number. The difference is in how the third layer is arranged. So the hexagonal closest packed, which is not a cubic unit cell, but it's a hexagonal cell. Here we have the first layer and the second layer, and the third layer is exactly the same as the first layer. So we call this an A-B-A pattern. This unit cell is hexagonal rather than being cubic. And so if you put those together and cut them up just right, we can see here that this is a hexagonal cell where we've got 120 degree and 60 degree angles instead of 90 degree angles. Cubic closest packed, we've got the third layer being offset from the first layer. Here's the first layer, second layer sits in the little indentations. The third layer is rotated so that this atom is not directly above its corresponding atom in the first layer. And this gives us a structure that is exactly the same as the face-centered cubic unit cell. So here's layer 1, layer 2, layer 3, and then this fourth layer would be the same as the first one. You stick those together, tip them on its side, get out a bandsaw and cut it all up, and you get that, and that's a face-centered cubic unit cell.